Welcome to the deep dive. We're here to take the sources you're interested in and we'll pull out the really key insights for you fast.
That's the plan.
Today, we've got the Beldex white paper version 3.1.2, dated September 20th, 2024. We're going to explore this decentralized ecosystem for confidential computation.
Right.
Our mission, essentially, is to get our heads around Beldex's approach to privacy. We're talking transactions, messaging, online activity, and the tech making it happen. You wanted the knowledge, quickly but thoroughly, without getting snowed under.
And it's a timely topic. The early idea that blockchains were automatically untraceable. That's long gone.
Absolutely. Blockchain analysis tools are pretty sophisticated now.
Exactly. These public ledgers, well, they can be analyzed. So Beldex is positioning itself as a strong, privacy-focused alternative.
Okay, so let's establish the basics.
Yeah.
Beldex is a proof-of-stake coin, uses masternodes.
Mhm.
What are the big advantages highlighted in the paper?
Well, they stress a few core things. Untraceable roots, stemming from a higher ring size in their RingCT, which we'll get into. Confidential transactions, obviously key. And they also mention things like airdrops for staking BDX.
Untraceable roots, confidential transactions.
Yeah.
Okay, let's unpack that. What's the foundation here? What are they building on?
It fundamentally builds on the CryptoNote protocol's ideas. So you're looking at ring signatures, RingCT, that's room confidential transactions, and stealth addresses.
Right, those core privacy technologies.
Yeah, they're not entirely new concepts in the space, but Beldex integrates and enhances them to achieve its privacy goals.
Okay, ring signatures, RingCT, stealth addresses. Quite the toolkit. Let's start with the transactions. The paper talks about untraceable transactions, emphasizing autonomy, like senders masking their own identity with cover traffic. How does that actually work when I send some BDX?
The core goal is making it incredibly difficult to link a specific transaction back to you, the sender. It's about breaking those identifiable chains.
Which is a big contrast to something like Bitcoin, right? Where if I keep using the same address, all those transactions pile up and point back to it.
Exactly. The white paper explicitly calls that out. A published Bitcoin address becomes an identifier linking payments. Beldex avoids that by generating a unique, one-time destination key for every single transaction output.
A one-time key derived from the recipient's address
And some random data the sender generates just for that transaction, so no address reuse.
Okay, walk me through it. Alice wants to send BDX to Bob. How does that actually happen step by step?
Okay, so Alice first gets Bob's public keys, let's call them A and B, from his Beldex address. Then Alice generates a secret random number, R.
Just for this one transaction?
Just for this one. She uses R, Bob's public key A, a standard base point G on the curve, and Bob's other public key B to compute a one-time public key. Let's call it P.
Okay, a temporary address P.
Right. P is the actual destination address for the funds in this transaction. She also includes R, which is just R times G, in the transaction data.
Got it. So Bob receives this transaction aimed at P. What does he do?
Bob scans incoming transactions using his private keys, A and B. He uses his private key A and the R value from Alice's transaction to do a related calculation. If the result matches the public key P used in the output, he knows that transaction is for him.
Ah, because only he could perform that calculation correctly with his private key A.
Exactly. And once he confirms it's his, he can then calculate the corresponding one-time private key X, which lets him spend those funds later.
So because P is unique every time, an observer watching the blockchain just sees funds going to all these different seemingly unrelated addresses? Makes linking payments to Bob much harder.
Precisely. And Alice doesn't know when Bob spends it either, because she doesn't have that private key X.
Makes sense. The paper also mentions a tracking key. What's that about?
That's the pair, A, B, Bob's private view, key A, and his public spend, key B. He could give this pair to, say, an auditor, Carol. Carol could then use it to see all incoming transactions destined for Bob, but she wouldn't have his private spend key B, so she couldn't actually spend the funds. Useful for auditing or maybe managing funds without full control.
Right. Visibility without spending power. What if Alice needs to prove she sent the money? Or Bob wants an audit-friendly address?
For Alice to prove it, she could reveal the random number R she used for that specific transaction. Or use a zero-knowledge proof to show she knows R without revealing it.
Okay.
For Bob, if he wants traceability for incoming funds, he could publish his tracking key, A, B, or what's called a truncated address, which is just the public key B. If he does that, incoming payments can be linked to him.
But spending remains private because he still needs B.
Exactly. Spending always requires the full private spend key, B.
Okay, that covers the unlinkability aspect pretty well.
Yeah.
Now, ring signatures. The paper says Beldex uses a fixed ring size of 11. What's the goal there?
Ring signatures are all about sender anonymity. It's like mixing your transaction in a crowd.
How does that work?
Imagine you have your actual public key representing the input you want to spend, and you grab, in Beldex's case, 10 other unrelated public keys from the blockchain. These are the decoys.
Okay, so 11 keys in total.
Right. You then create a signature using your private key, but mathematically incorporating all 11 public keys in the ring. Anyone verifying the signature can confirm that one of the 11 keys corresponds to the private key used, but they absolutely cannot tell which one it was.
So the real sender is hidden within that group of 11, like the digital police lineup analogy. You know someone in the group did it, but not who.
That's a pretty good way to think about it. It provides signer ambiguity.
What are the crucial properties of these ring signatures for privacy?
The whitepaper flags three main ones. First, signer ambiguity, we just covered that, hiding the real signer. Second is linkability.
Linkability, doesn't that contradict anonymity?
Not quite. It means if the same private key is used to sign two different messages, or transactions in this context, those signatures can be mathematically linked. Beldex uses this property to prevent double spending the same input.
Ah, so you can't scan the same coin twice because the signatures would be linked, revealing the attempt. Clever. And the third property.
Unforgeability. Pretty standard for digital signatures. You can't create a valid signature without the correct private key. Basic security.
Okay, linkability prevents double spending while ambiguity provides anonymity. Now, the paper mentions one-time ring signatures for unconditional unlinkability. How are these different?
Yeah, so the idea with one-time ring signatures is to go a step further and ensure that even if the same person sends multiple transactions over time, analyzing those signatures doesn't reveal any link between them. Each signature is cryptographically unique and independent.
So even stronger unlinkability than just using different output addresses.
Exactly. The paper briefly mentions the algorithms involve GEN for key generation and the key image, SIG for signing, VER for verification, and LNK for checking that linkability aspect for double spending. We don't need to dive deep into the math, though.
Right, but you mentioned a key image, IXHP. That sounds important. What is it?
The key image is crucial for that double spend prevention without revealing the signer. Think of it as a unique tag derived from the specific output being spent using the one-time private key X and a hash of the one-time public key P.
A tag for the spending event?
Precisely. Every time a specific output is spent, it generates the exact same key image. If someone tries to spend it again, the network sees that key image pop up a second time and knows it's a double spend attempt.
Gotcha. So key image double spend detection. The paper then throws in BLSAG and MLSAG. Just advancements on this?
Yeah, essentially refinements. BLTAG-backed linkable spontaneous anonymous group signature improves things, so the linkability property is independent of the specific decoys chosen for the ring. Makes it even more robust.
Okay. And MLSAG?
MLSAG, multi-layer linkable spontaneous anonymous group signature, is designed for situations where a transaction might have multiple inputs. It allows signing for multiple private keys, representing multiple inputs, in a single signature structure.
So if I'm combining funds from several previous transactions?
Right. And crucially, the linkability property still holds if any of the private keys used in one MLSAG signature are used again in another. Those signatures will be linked. Yeah. It handles complex cases while maintaining that double spend protection.
Okay, these advanced signatures seem to boost anonymity, especially for more complex transactions. Now let's revisit stealth addresses. We talked about one-time keys, but how do stealth addresses specifically help the receiver's privacy?
Stealth addresses add another layer of obfuscation specifically for the recipient. Instead of Bob giving out his main public address, AB, Alice uses it, along with her random data R, to compute that one-time public key P.
Right, the temporary destination.
P essentially functions as a stealth address. It's an intermediary address. Funds go to P, and only Bob, with his private keys A and B, can derive the corresponding private key X to spend the funds later.
So Bob's main address, AB, never actually appears on the blockchain as receiving funds.
Correct. An observer just sees transactions going to these unique, seemingly random P addresses. It breaks the link between different payments received by Bob.
How does that key generation part work, the Diffie-Hellman exchange?
Yeah, it uses a Diffie-Hellman key exchange mechanism. Alice uses her random number R and Bob's public keys, AB, to compute a shared secret. Bob uses his private key, A, and the R value, RG, from the transaction to compute the same shared secret. This shared secret is then used to derive both the one-time public key and the one-time private key X.
So they can independently arrive at the keys needed for the transaction without revealing their main secrets? Neat. Okay, hiding sender, hiding receiver. What about hiding the amount? That's where RingCT comes in.
Exactly, ring confidential transactions or RingCT. Even if you don't know who sent or received, knowing the amounts, especially patterns in amounts, could leak information.
Right, like if I always buy my coffee for the exact same amount, maybe someone could connect those transactions over time.
Precisely. RingCT hides the transaction amounts completely.
How? The paper mentions Peterson commitments.
Peterson commitments are a cryptographic technique. They let you commit to a value, say, the transaction amount, without revealing the value itself. But crucially, they have this property called additive homomorphism,
Meaning?
meaning if you have a commitment to amount X and a commitment to amount Y, you can add the commitments together, and the result is a valid commitment to the amount X plus Y.
Yeah.
Beldex uses these, incorporating a secret blinding factor into the commitment. This factor mathematically hides the actual amount. It uses elliptic curve math with a second generator point H to make it information theoretically hidden.
So the amount is masked. But if all amounts are hidden, how does the network stop someone from just creating BDX out of thin air in a transaction? How does it check that inputs equal outputs?
That's where the additive property is key. While individual amounts are hidden, the network can verify that the sum of the input commitments minus the sum of the output commitments equals a commitment to zero.
A commitment to zero.
Yes. The sender, knowing all the amounts and blinding factors, creates a cryptographic proof, part of the transaction signature, demonstrating that this balance holds true, that inputs equal outputs plus the fee without revealing any actual amounts.
Wow, okay. That's clever. But what about negative amounts? If everything's hidden, could someone theoretically create an output with a negative amount to balance things?
That's a potential issue with basic commitments. That's why Beldex uses range proofs.
To prove the amounts are positive.
Exactly. Range proofs cryptographically demonstrate that each hidden output amount lies within a valid range specifically, between 0 and a very large positive number, 264.1. Beldex uses a complex method called the Borromean signature scheme for this.
Yeah.
It effectively proves each bit of the amount is valid, guaranteeing the amount is non-negative.
Okay, so commitments hide the amount, the additive property ensures balance, and range proofs ensure the amounts are positive and valid. Quite a system. Now, let's tie this back to the user's keys and addresses. We know there's a view key pair, KV, KV, and a spend key pair, KS, KS, and the address is the pair of public keys, KV, KOS. How does this play out in a typical transaction?
Right, so as we discussed, the public address, KV, isn't where funds are sent directly. Alice uses Bob's, KV, KS, and her random data to generate that one-time address, P.
And Bob uses his private view key, KIV.
To scan the blockchain.
Yeah.
He uses KE and the transaction data, like R, to check if P was derived using his public view key, KS. If it matches, he knows the transaction is for him. But he needs his private spend key, KS, to actually derive the one-time private key X and spend the funds later.
So view key sees incoming, spend key actually spends. Got it. What about multi-output transactions? The paper mentions an output index.
Right. If Alice sends BDX to Bob, and also sends some change back to herself in the same transaction, both outputs need unique one-time addresses. The output index, basically just 0 for the first output, 1 for the second, etc., is included in the calculation for P.
So even if the recipient, like Bob's main address, is technically the same for multiple outputs in one transaction, adding the index ensures the derived P values are different for each one.
Exactly. Prevents accidental linking within a single transaction.
Makes sense. Now, subaddresses and integrated addresses sound more like user-facing features. What's the deal with subaddresses?
Subaddresses are a way for Bob to generate many different receiving addresses that all funnel funds back to his main account, controlled by his single set of view spend keys.
Why would he do that?
Organization and privacy partitioning. Bob could give one subaddress to Alice for that Apple purchase, another to Charlie for something else. He could track payments easily, but externally, it's very hard to link those different subaddresses back to Bob's main address or to each other.
Like having multiple P.O. boxes that all lead to the same place?
Good analogy, yeah. Keeps different activities separate from an outside perspective.
And integrated addresses. They include a payment ID.
Yes, an integrated address bundles a short payment ID directly into the address string itself. Useful if Alice needs to include, say, an invoice number when paying Bob.
How is that kept private?
The payment ID is encrypted using that same Diffie-Hellman shared secret derived from Alice's random data RD and Bob's view key, KE. Bob can then use his view key to decrypt the payment ID when he scans the transaction. It's a convenient way to attach metadata securely.
Okay, convenient and private. Finally, for transaction types, the paper mentions RCT type full and RCT type simple and says RingCT is now mandatory.
Correct. RingCT is the standard now. RCT type full was the initial main type aiming to replace older formats. RCT type simple came later to address a specific potential traceability issue with multi-input RCT type full transactions.
Okay, let's tackle RCT type full first. Used mostly for single input transactions now, you said. How does the receiver actually reconstruct the amount sent to them?
In RCT type full, the output includes a masked amount and a masked value. Bob, the receiver, uses the shared secret, derived via Diffie-Hellman, using his view key, key AV, to essentially reverse the masking process Alice applied. This reveals the original blinding factor and the actual BDX amount sent to him. He can then check if this matches the Peterson commitment included in the output.
And the commitment to zero we talked about, how does that work here to ensure balance?
Right. The core idea is that the sum of input commitments should equal the sum of output commitments plus the fee commitment. In RCT type full, the sender creates a special signature, an MLSAG signature actually, that proves this relationship holds, effectively proving the transaction balances to zero without revealing the values. This uses a specific point ZG representing that commitment to zero.
What exactly is being signed in that MLSAG signature?
The sender forms a ring, including their actual input commitment and several decoy commitments chosen from the blockchain. The signature proves they know the private key corresponding to one of the commitments in the ring, their input, and it also implicitly verifies that commitment to zero balance. It signs a hash of the transaction message. Importantly, the part verifying the commitment to zero doesn't use a key image. Range proofs, Borromean, are also included for each output.
How is the transaction fee handled in this balance check?
The fee amount itself is actually sent in the clear, unencrypted. When the network verifies the transaction, it checks that. Sum of input commitments, sum of output commitments, commitment to zero, ZIG. The fee commitment is just the fee amount F times that second generator H, so FH.
Okay. Now, you mentioned a traceability issue with multi-input RCT type full transactions related to key images. Can you elaborate? Why stick to single input mostly?
The problem is, if the same key image appears twice, a double spend attempt, it could potentially reveal the index of the real input within the ring for both those fraudulent transactions.
And that leaks information.
Yes, because it could imply that other inputs at that same index in those rings might also be real spends, de-anonymizing them. Furthermore, an analyst might deduce that in all RCT type full transactions, the real inputs tend to share the same ring index. This weakens the anonymity. Limiting it to single input largely avoids this specific weakness.
That makes sense. Protecting privacy even against potential future analysis. So that leads us to RCT type simple for multi-input transactions. How does it differ?
The key difference is that in RCT type simple, each input is signed independently. There isn't one single signature covering all inputs. This avoids the shared index problem of multi-input RCT type full.
But if inputs are signed separately, how do you ensure the whole transaction balances inputs equal outputs plus fee?
It uses a concept called pseudo-output commitments. For each input, the sender creates a new commitment to the input amount, but using a different, fresh blinding factor. Let's call the original input commitment K and the pseudo-commitment CA. The difference, CTA, mathematically acts like a commitment to zero for that specific input. The sender then carefully chooses all the blinding factors for inputs, pseudo-commitments, and outputs so that the sum of all the pseudo-input commitments equals the sum of the actual output commitments plus the fee commitment.
Wow, okay, so each input gets its own mini balance check against a pseudo commitment, and then all the pseudo commitments balance against the real outputs and fee.
Exactly. It's a bit more complex algebraically, but it achieves the balance.
And the signature process for RCT type simple.
For each input, the sender creates a separate MLSAG signature. The ring for signing input J includes decoy outputs from the blockchain, plus the pseudo-output commitment CA created for that specific input. The signature uses the private key for input J. Since each input is signed in its own ring, the real inputs don't share an index, solving the traceability issue. Borromean range proofs are still used for the actual outputs.
It sounds like RCT type simple sacrifices some, maybe, compactness for stronger multi-input privacy. What about transaction size and verification effort compared to type full?
Generally, yes. An RCT type simple transaction with multiple inputs will likely be larger than a comparable RCT type full if it were used for multi-input. Could you have a separate MLSAG signature for each input, plus the pseudo commitment.
In verification.
Verification also takes more computation because the verifier needs to check each of those individual input signatures, along with the range proof for the outputs. So there's a trade-off: size and computation time versus enhanced privacy for multi-input scenarios.
Okay, that gives a really solid understanding of the transaction mechanics. Let's zoom out to the blockchain infrastructure, starting with masternodes. What's their role?
Masternodes are essentially the backbone nodes of the Beldex network. They're full nodes that are incentivized to provide higher levels of service and reliability.
Incentivized how?
You need to lock up significant collateral, 10,000 BDX currently, and meet specific bandwidth and storage requirements. This stake acts as a guarantee of good behavior. In return, they get a large share of the block rewards, 90% in fact.
90%. Wow, so they're crucial for
Functionality and scalability. They participate in proposing and validating blocks under the proof-of-stake system. They support the Flash instant transaction layer, maintain parts of the Belnet routing table, and generally ensure the network runs smoothly.
How are those block rewards distributed fairly among all the masternodes?
The current reward is 6.5 BDX per block, roughly every 30 seconds. 10% goes to the node that actually constructed the block. The other 90% goes to the masternodes via a queue system.
A queue.
Yeah, basically, once a masternode gets paid, it goes to the back of the line. The ones who've waited the longest move to the front. Ensures a fair distribution over time.
With Beldex being so private, how does a masternode prove it holds the 10,000 BDX collateral without revealing its total balance?
Through authenticated collateralization, they have to perform a special transaction to time lock exactly 10,000 BDX for a long period, 86,400 blocks. This lock is visible on the chain, even if the source of funds isn't fully revealed by ring signatures in the locking transaction itself. Existing masternodes verify this lock before accepting a new node. The BDX is unusable while locked.
So the lock itself is the proof, not revealing the whole wallet. Clever. The paper also mentions Flash instant transactions. What's that?
Flash is Beldex's Layer 2 solution for near-instant payments. Think seconds, not minutes.
Like Bitcoin's Lightning Network.
Conceptually similar, yeah. It uses payment channels off-chain. Masternodes play a key role here by forming quorums to quickly validate Flash transactions and, crucially, lock the key images of the inputs being spent.
Locking the key images prevents double spending on the Flash layer.
Exactly. Before the transaction hits the main blockchain, the masternode quorum confirms the inputs haven't already been spent in another Flash transaction.
And there's a coin burning mechanism tied to Flash.
Yes. A portion of the fees generated by Flash transactions are permanently burned, removed from circulation. This acts as a deflationary pressure to help control BDX inflation over the long term.
Okay. Now the big shift. Proof of work to proof of stake via the Bucephalus hard fork. Why the change?
Primarily energy efficiency. Proof of work is incredibly energy intensive. Proof of stake, POS, offers a much greener alternative. Instead of competing with computing power, nodes are chosen to validate blocks based on the amount of BDX they've staked or locked up.
How does Bucephalus POS work in Beldex specifically?
You need at least 10,000 BDX to stake. Every 30 seconds or so, a staking node is randomly selected to propose the next block. That proposal then goes to a randomly selected quorum of 11 other validator nodes.
And they vote on it?
Essentially, yes. If at least 7 out of the 11 validators agree the block is valid, it gets added to the chain.
The energy savings must be significant compared to POW.
Hugely significant.
Yep.
POS validation is computationally very lightweight compared to POW mining. It decouples security from raw energy burn.
How secure is this model? What stops a big stakeholder from messing with the network?
The main security comes from the cost. To attack the network, you'd need to control over 50% of all staked BDX. Acquiring that much would be extremely expensive, likely prohibitively so.
And there are penalties.
Yes, slashing. If a validator node misbehaves, tries to double sign, goes offline for too long, a portion of their staked 10,000 BDX can be automatically forfeited, a strong economic disincentive to cheat.
The paper also mentions checkpoints, another security layer.
Right. Every 4 blocks, the network creates a checkpoint, basically a signed hash representing the state of the chain up to that point. This makes large-scale history rewrites, reorgs, much harder, as an attacker would have to somehow invalidate these agreed-upon checkpoints. It limits the potential damage from a temporary compromise.
Like saving your progress frequently. Okay, the Bucephalus hard fork, December 10th, 2021. Key changes again were
POS activation, block time down to 30 seconds, smaller transaction sizes, higher block rewards, and the launch of Flash, a major overhaul.
And it uses different quorums running simultaneously.
Yes. There's the main POS quorum for block proposal and validation. a separate flash quorum, actually two groups working together, for validating instant transactions, a masternode quorum that monitors node uptime and eligibility, and the checkpoint quorum that creates those blockchain snapshots every 4 blocks. Different groups of nodes handling different critical tasks concurrently.
What about handling failures? Byzantine Fault Tolerance. What if a block isn't produced on time?
BFT is about ensuring the network reaches consensus, even if some nodes fail or act maliciously. If a block producer fails, or not enough validators participate or agree, the system has mechanisms to move on. The next producer can flag the failure. Validators can issue intent to demerit messages against non-performing nodes, leading to potential penalties or even decommissioning if violations persist. There are rules for handling various fault scenarios.
So multiple layers of redundancy and fault handling built in. Okay, let's shift to the ecosystem built on this tech. Wallets.
They offer decentralized wallets for Android, iOS, and desktop via Electron. Standard stuff: store, send, receive BDX, view history. The desktop one also helps users set up masternodes. Mobile staking is planned too.
And BChat, the messaging app. How is it private?
BChat focuses on anonymity. It routes messages through Belnet, their decentralized VPN. It uses end-to-end encryption, sure, but crucially, messages hop through at least 3 intermediary Belnet nodes.
Hiding the origin and destination.
Exactly. No central server store messages, and the multi-hop routing via the DVPN makes it very hard to trace who is talking to whom.
Tell me more about Belnet, the DVPN itself.
Belnet uses the Beldex routing protocol, BRP. It's like Tor or I2P in concept, using onion routing principles, data packets wrapped in layers of encryption, peeled off at each hop.
Decentralized infrastructure.
Yes, the routing directory, a distributed hash table or DHT, is maintained by the masternodes. To run a relay or exit node on Belnet, you need sufficient bandwidth and have to stake some BDX. Their performance is monitored, with penalties for unreliable nodes. The aim is censorship resistance and privacy beyond typical centralized VPNs.
And the Beldex browser?
It's designed as a privacy-first browser that routes all its traffic through Belnet by default. The goal is to combat online tracking and give users more control. They even envision models where users could potentially pay creators in BDX for ad-free experiences.
Interesting. A whole suite: blockchain, messenger, DVPN, browser, all focused on privacy. What about the community aspect?
They emphasize community engagement across many channels: Telegram, Twitter, Discord, etc. Contributing mainly involves running a masternode or staking BDX. For developers, the code is open source, accessible via Discord. They also mention having allocated 80,000 BDX for bounties and airdrops to encourage participation.
It seems like they're trying to build both the tech and the user base. Okay, that pretty much covers our deep dive into the Beldex white paper.
Yeah, what stands out is how they've layered these different cryptographic techniques. Ring signatures for the sender, stealth addresses for the receiver, RingCT for the amount. It's a multi-pronged approach just for the transaction privacy.
Right.
And then extending that philosophy out to messaging with BChat, browsing with Belnet and the Beldex browser. It's quite ambitious.
So, quick recap. Beldex aims for untraceable transactions via ring signatures, unlinkable payments using one-time addresses, hidden amounts with RingCT, and receiver privacy through stealth addresses. The goal seems to be a comprehensive, privacy-centric ecosystem.
Which leads to a final thought for you listening. As digital privacy keeps becoming more and more critical, how might these kinds of decentralized, privacy-focused ecosystems like Beldex change how we interact online and what we even expect in terms of privacy?
Definitely something to think about, and maybe dig into the Beldex resources further if you're curious.